baseline levels, if we have some concerns about water quality at some point, then there are some numbers we could compare with to understand, is it normal levels, for example, for Nile elevation. Mainly the two ones, which are easily to identify: the land cover from Korean land cover, because it's already harmonized between the countries and easy to use. And from there, we understood that it's the area dominated by forests, and then followed by agricultural lands, and also in small portion, but still wetlands. So we need to include this quaternary, the upper layer, because it's very important. And the population density is very low in that area, especially if we compare to the other world. And the groundwater consumption also is very moderate. And if we look at the graph, we see that in the last decade, it has not changed much. So there are no significant trends we should look at. So it's rather pristine area with evenly distributed pressures. And this is the final result, the conceptual understanding of the territory, where we show from where to where the flows are flowing. So probably where should be some hotspots, like major groundwater obstruction points or some point source pollution. And basically, the main outcome is that the area is rather pristine and there are no significant pressures to address at the moment, at least as we know. What we will do in the future, we will develop a transboundary monitoring network. And for that needs, for gathering more data, this conceptual understanding is vital. So it is expected that in some areas we will miss monitoring points from the existing networks. And installation of new wells is very time-consuming, resources-consuming, and you need to maintain it. So we are looking for identification of possible springs to be included in the network. They are already there. You don't need to maintain them, and you don't need to pump, so it's cheaper. But the only thing what is needed is this preliminary screening and the delineation of catchment areas. So whether the spring represents local conditions or already regional ones. And before I conclude, apart from all the statistics and graphs and what also takes a lot of time and the knowledge, the most important part is the collaboration itself. So basically to jointly protect groundwater resources, it is important to develop a trust. So basically we often need to share sensitive data. Sometimes we need to face that maybe we are not doing the monitoring, for example, in the best possible way. Maybe we should improve ourselves. So it takes a lot of willingness to change and find compromises. If we especially talk about harmonized monitoring, we need to decide on the same equipment or on the same approaches and analytical methods. And of course, we need to devote time and human resources, whether we are the taker and learning or whether we are the giver and teaching the other side. So I think this is even the most important part in everything. So thank you for your attention. And if you want to know more, there are like the parallel session coming out, and from the project, there are other speakers in other sessions, but you can follow our project upcoming news and also the social media. Thank you.
Thank you very much, Inga. Very interesting presentation, and what you are saying in the conclusion is really true. And I experienced it myself in the Middle East when working with Israeli and Palestinian people. We had to check with both parties every data point, every reading, every water level reading, in order to have a common data set. And from that, we can hope for finding common approaches and compromises. Thanks a lot for this sharing with us. I think we can move to the next presentation, which will be, is Mr. Gamal Abdo here? No, I don't think he is able to present the next presentation, which was forecasted related to Sudan. So we skip and we go to the next one, which is a presentation by Mr. Samuel Sunguru about hydrogeology of the Eastern Kalahari-Karoo Transboundary Aquifer Basin. And Mr. Samuel Sunguru is working with the University of the Western Cape, where he's PhD candidate, and I know that he's also a private consultant from Zimbabwe. So, Mr. Sunguru, this is for you to present your talk. Thank you.
Thank you, Chair. Thank you, colleagues. My name is Sam Sunguru, has already been said by the Chair. Colleagues, I'm going to present on the hydrogeology of the Eastern Kalahari-Karoo Transboundary Basin Aquifer, abbreviated EKKTBA. This is actually a culmination of a project implemented by various experts whose faces and names are actually given in the slide. You can actually see the various experts. And it was actually commissioned by the SADC-GEMA in 2020 and financed by the World Bank. The scope and purpose of the project was, one, to provide information and data and its analysis for the sustainable management of the EKKT-based water resources. Number two, enhancement of the riparian states to collaboratively and effectively manage the EKKT-based water resources. And thirdly, it was to feed into the transboundary diagnostic analysis, the TDA, and the findings of the TDA were actually presented by my colleague, Dr. Hans Bickman, yesterday. And you can actually see that the basin actually straddles Zimbabwe and Botswana, running from Western Zimbabwe into Eastern Botswana. And the delineation of that boundary was also discussed by Dr. Beckman yesterday. And we collected data. The acquisition of the data was through peer-reviewed publications, technical reports from the riparian states, and the consultancy expertise and knowledge of the region. But we had challenges with the quality of the data, the amount of the data that was available, and also accessibility to that particular data. The climate, this is a semi-arid region, and but we only have a few observation stations in the basin, and we had to complement the data using data from the Climate Research Unit. But before we could utilize the data, we had to check for its accuracy, and we compared the data from the observation stations. And you can see actually from the right side where my case is that it fits fairly well. And as such, we can actually utilize the data from the CRU, the Climate Research Unit, and you can see from the top image that temperatures actually increase as we move from Zimbabwe into Botswana, and rainfall is actually vice versa. The topography is generally flat, and the hilly part is only in the eastern part of the basin where my cursor is, or the pointer is, and we're looking at gradients of around 4 per mil. But the rest of the basin, we're looking at 0.2 per mil. And the rivers are mostly ephemeral, and the only perennial rivers are in the eastern part of the basin, and these actually flow into the Zambezi River. And we've got the Makhalkhali pans, which are actually in the southern part or southwestern part of the basin, and here we have elevations or altitude of around 880 meters above sea level. So base flow is negligible, and rivers, when they do flow, they're generally fresh, but as they get into the Makhalkhali pans, they become saline, which is actually obvious. And the next slide actually looks at the stratigraphy and structural geology of the basin. The figure on the left, we try to simplify the geology for ease of understanding. And if you look at the one on the right, it was for the correlation of the Karoo supergroup units. And you can actually see that from the Arones Basin, which is in Namibia, all the way to the Mid-Zambezi Basin in Zimbabwe, cutting through Botswana, we have got a good correlation of lithological units. And also it tells us that it's quite widespread, and we've got deep-seated aquifer systems and the multi-layered aquifer systems as well. If you look at the image at the left, you see the yellow color that represents the Kalahari aeolian sands, which are essentially unconsolidated. And the lines, these are cross-sections, which I will talk about later on. If you strip off the Kalahari sand, you actually end up with the image on the right, where we have got pre-Kalahari formations in the form of Kalahari, in the form of Karoo formations. We have got the basalt, which is the H1. We have got, this is the sandstone, which I'm indicating. And this sandstone is the one that is of interest to us because it forms the main aquifer system within the basin. And it's actually known as the forest sandstone in Zimbabwe and Trentane sandstone in Botswana. The next slide just shows the effect of the structural features, how they actually control the hydrogeology of the area. We have actually deep-seated formations which have actually been thrust to the surface. We've got a lot of faulting that occurred. So this has got a bearing on, strong bearing on groundwater flow, groundwater quality, as will be noticed later. And these are the cross-sections that I alluded to earlier on. You can actually see that we, from the first diagram and the other cross-sections, that we've got a lot of block faulting within the basin, and this actually complicates, the whole hydrogeology of the basin. If I move on to the issue hydrogeology, general hydrogeology, what we have, if you look at the image, we have got where I've got these yellow dots and where I'm moving my cursor. These are the well fields, and these well fields, they actually developed along the fringes of the basin. Why? It's because the groundwater is actually fresh around there. And we have got detailed information in terms of our hydrogeological investigations carried out for the various well fields. And if we project that information now onto the basin, we can actually tell that the groundwater actually flows from the fringes of the basin towards the Makhalkhali ponds, which actually act as the discharge area. And we also know that, groundwater salinizes rapidly as we move away from the fringes towards the central portions of the basin, and also with increasing depth. Recharge, we know it comes from direct and indirect, by direct and indirect mechanisms. And we have got hydraulic characteristics, and we are looking at unconfined, semi-confined to confined aquifer conditions. And this slide just emphasizes the rapid salinization of the groundwater, as I said earlier on, with increasing distance from the fringes and also increasing depth. You can see that for this particular area, this is a distance of about 20 kilometers, and the TDS actually increases from less than 500 milligrams per liter to more than 2,000 milligrams per liter. The next slides talk to issues of recharge. There have been numerous groundwater recharge studies carried out in the Southern African region. And you can actually see that for the same amount of rainfall, we've got varied recharge rates. I mean, this could be issues of preferential recharge, which actually takes place if you notice in certain areas where for the region is actually typified by huge faulting, fracturing, and all that. If we linearize the data now, we get the image on our right, where here, and you would realize now that the data from the Southern African region is actually enveloped within one standard deviation. But if we pull out data from the study area from the EKKT Bay, the data is actually enveloped within half a standard deviation. And also you can notice that there's a threshold where groundwater recharge will not actually take place. And if you look in this particular figure, we're looking at 350 millimeters per year. If the rainfall is below that, we don't expect any recharge to occur. And the relationship now for the EKKT Bay of recharge and rainfall is actually given by is given below the figure. And if you apply that relationship to the rainfall distribution within our basin, we actually end up with such a ground recharge potential map. And you can see that recharge increases from the southern western part of the basin to the northeastern part of the basin. And this is just to give us the hydrogeological outlay. And after synthesizing all the data, you can actually see that, we have got a recharge taking place on the peripheries. We've got deep-seated groundwater, shallow-seated groundwater in terms of the aquifer systems. We've got a lot of faulting and block faulting, a lot of doleric intrusions within the area. If I move on to groundwater abstraction and use, this is from the various, the graphs are from various well fields. You can see from the Duke well field in Botswana, we have some missing data, but generally there is an increase in abstraction. In Zimbabwe, in Yamalov area, where I'm actually showing the laser pointer, we have missing data, and also a lot of abstraction is taking place. But the issue now is because this is a semi-arid region relying on groundwater, this data will be actually essential in the management of the aquifer system. So these are the issues which have to be attended to later. And you can actually see, as represented by the Lehlekane well field, where I'm pointing that the water demand outstrips the supply. And this is actually increasing on a yearly basis, and the shortfall is actually widening in terms of the amount that is actually required. If you look at the pie chart, it gives us sectoral use of the groundwater, and about 2/3 of that is actually consumed by the mining sector. And if I go back to now, and if Ponds 2007 suggests that you can safely take 40% of your average annual recharge as representing a sustainable groundwater recharge, if you apply that to the groundwater recharge map I showed earlier on, you come up with such a map. And we have tested results obtained from the map for two areas, the Nyamalov area in Zimbabwe. Beckman and Sunguro in 2015 carried out, using groundwater modeling and other techniques to investigate daily sustainable recharge. They come up with a figure of 15,000 cubic meters per day. And if you compute from the map, you get 14,400 cubic meters per day. And that fits well. And for Dukwe, which is here in Botswana, you are looking at a figure of 400 cubic meters per day as obtained by the Department of Water Affairs in 2000. And from the map, you get a figure of 470. Again, it fits well. But what I should emphasize on is that the recharge area has to be understood so that you are able to compute the daily sustainable abstraction figures. That's number one. Number two, this map is not actually the end to it or the panacea to everything. The issue is in our region, normally, groundwater development supersedes or precedes rather any investigation. So this can actually be used as a first port of call in understanding what are we actually looking at in terms of sustainable abstraction rights. And in terms of future development, you can see the areas encircled in red. These are areas which can actually be further developed to enhance water security in the region. But we also have to look at other strategies such as managed aquifer recharge. You also have to look at water conservation. In this area, you have to look at innovative irrigation methods, water demand management, strategies, so that you are able to optimize the utilization of the water that is actually available at the moment. And when it comes to management and monitoring, as I pointed out earlier on, this is a basin which has just actually been investigated, but there's no groundwater management unit. And it's one of the areas which has to be addressed. For you to be able to manage, you need to have a body to do that. So the regional institutional framework of the SADC actually allow for the creation of such a unit. And if I can move on, you can notice that monitoring is actually restricted to the peripheries, obviously, to the well fields. And there's nothing in the hinterland. And there's need to really understand what is actually going on. So there's need to actually expand the monitoring so that areas which are not covered are actually covered. And also, there is isolated, monitoring events. There's no synergy between the various work fields. So these are other areas which need actually to be looked at. So there's expansion and the synergizing of all these. And as a way forward, we looked at issues of establishment of the management body, groundwater management body. We looked at issues of capacity building, because once you actually set it up, you need people, the people need skills, and they need resources to be able to carry out their respective responsibilities. And there's a comprehensive monitoring program which looks at water levels, subtraction, water quality, rainfall, and there's need for data and information management. I mean, from data acquisition protocols, for quality control, quality assurance, issues of databases, friendliness of the database to use, and how to gather additional information from other resources like CRIU, GRACE, and issues of data sharing is also critical. Management, water management issues, they have to be looked at, issues of conjunctive use, management after recharge, and also for us to have an appreciation of actually what is going on, we need a regional basin groundwater model. With that said, I would like to express my deepest appreciation to SADC GMI staff who made the project possible, and the focal persons from the various representing states were actually instrumental in actually acquiring some of the data, though it was difficult in certain instances, and the river basin organizations involved, because this transboundary basin actually transcends two surface river basins, surface water river basins, and also the participants in the workshops. With that, I thank you. Merci beaucoup. Gracias. Domo arigato.
Thank you very much, Samuel. It's a very nice presentation, comprehensive and interesting work that you have shown us. Particularly regarding the groundwater recharge estimates that you have carried out, and from which you were able to elaborate this map regarding the potentiality, which could be potentiality in sustainable abstraction, which could be a very useful tool for decision makers. That's something which could inspire other studies. Thanks a lot. Now I need to apologize because I skipped one of the speakers, so I'm very sorry. I will give him the floor right now. It's Dr. Azizallah Izadi, who's from Sultan Qaboos University, who is leading researcher at the Water Research Center, and he will present his talk about sustainable transboundary groundwater management using groundwater modeling and hydrochemical investigations. Dr. Izadi, it's your turn. Thank you.
Thank you so much, Dr. Alexis. Hello, everyone. My name is Azizallah Izadi. I'm working in Water Research Center, Sultan Qaboos University in Oman, Middle East, and this presentation that I will present in coming slides, it's related to my postdoc period back in 2015. And the title of my presentation will be Sustainable Transboundary Groundwater Management Using Groundwater Modeling and Hydrochemical Investigation. Before presenting my project, my study, I will highlight about the importance of modeling and why we need modeling for transboundary aquifers. The management of transboundary aquifers is very challenging because of many interconnected aspects, such as political, institutional, socioeconomic, and cultural differences. And because of this, we need integrated management, which indeed we need in knowledge about institutional, social, economic, environmental, and the characteristics of the transboundary aquifers. The question is here how we can accomplish sustainable development in transboundary aquifers and what are the components of the integrated management. The one solution maybe is this, that for integrated management of transboundary aquifers for smoothly sustainable development, we need four main aspects. As you can see here, we need technical tools, policies, institutional framework, and human resources. In fact, we as researchers and scientists are providing technical tools for decision makers to make some policies. But what is the relation between technical tools and policies here? As you can see here, we as scientists and researchers, we are processing raw data through technical tools. And then the outputs of technical tools, we are extracting some high-priced information. Then decision makers can use this high-priced information for making some policies. In fact, some wise policies. With this brief introduction about the importance of technical tools for decision makers, I conducted a research project for Oman UAE border near Al Buraimi name region, just to provide some developing decision tools to extract high-priced information for policymakers. The reason for conducting this research was three main reasons. The one was the substantial development of irrigation, irrigated agriculture and city expansion. You can see here that this polygon is related to a study area. And here we have Oman, and here we have this side. In fact, the west side is UAE side. And you can see that here we can city expansion, we can see clearly. And this is the 1996, and this is 2013. And also the importance of groundwater resources as a source of drinking and irrigation water. In fact, we know that we have heavy abstraction in UAE site here. And we have groundwater level decline of 10.5 meter over 17 years. It means 62 centimeter per year. And when we see this map, we can see that the North Oman mountains here, they are acting as a recharge zone. And this side, the UAE side, they are acting as a discharge zone, and they are using the water coming through the border of Oman. And about the study area, if we did the groundwater modeling and hydrochemical investigation, the area is about 1,600 square kilometer. The average rainfall is around 82 millimeter, and it is ranging from 30 to 178 millimeter. Maximum daytime temperature may reach 50 degrees Celsius in the summer month, and it is quite high and long term. And because of this high temperature, we have long-term annual potential evapotranspiration is about 2,700 millimeter. And because of these challenges and because of the critical needs, we did integrated modeling and hydrochemical approaches to assess the groundwater behavior in the Oman UAE transboundary aquifer. The first part for developing groundwater conceptual model is a 3D stratigraphic model of the study area. Because of this, we collected a lot of data, and around 100 boreholes that we had in area, And by using these boreholes, we made some cross sections, and from these cross sections, we generated this stratigraphy map that you can see that we have 4 main hydrogeological units as alluvium, tertiary, ophiolite, and hawasina. Alluvium is clear, tertiary is about ocean sedimentary, and ophiolite is about also ocean. And in the second step for groundwater modeling conceptual model, we use different interpolation methods to figure out which method is suitable for our area. And we understood that Bayesian kriging method is the best method for interpolating groundwater level data. You can see that groundwater flow from east to west, it means from North Oman mountain, that you can see the green color, and it is recharging from North Oman mountain to discharge zone, that it is Oman UAE side. And as I mentioned in previous slide, the groundwater decline is about 62 centimeter. And also through this study, we optimized the monitoring network for the study area. After that, for the conceptual model, we estimated the groundwater recharge through water table fluctuation method. In this study, we proposed a new novel method through combining water table fluctuation method and water balance method, and we estimated groundwater recharge for the study area. And after that, when we completed the groundwater conceptual model, we developed groundwater numerical model. We used, in fact, this generated stratigraphy to define layer elevations and materials. And then we mapped, developed conceptual model to simulate groundwater flow. You can see that we subdivided some units for alluvium and also for hard rock. And for the groundwater model, numerical groundwater modeling, we did a fully transient simulation from 1996 till 2013 for quite long period. And also we considered the monthly time step, stress period, and time unit. And also we used the finite difference method with 500 meter cell size in the model. For the boundary conditions, we used no flux boundary for the eastern part of this part of the study area because of surface water and groundwater divide. And also we considered for the northern and southern part of the study area, no flux boundary because of the boundary is parallel to groundwater flow. And finally, for this is the border of Oman and UAE. We considered a specified head boundary condition. And after calibration of the groundwater model, and we understood that the model is calibrated quite well. You can see the performance criteria or statistics for here, and we calibrated the model for 2000 September. You can see here the observed and the computed groundwater level, that they are quite matching each other. And also here you can see that the same map for the validation period that it shows September 2013. When we are looking at the table for model performance statistics for the validation and the calibration, maybe you may say that it is quite high, but based on the study area and also the resolution we had, and 39 observation wells, and the most important part is the interconnecting between hard rock and the alluvium part, it was quite satisfactory. The most important finding of this study, it was this in fact, the modeling part of the study was this table that you can see that we differentiated between different climates. We have here wet climate, normal climate, and dry climate. And we estimated long-term regional sustainable groundwater extraction or safe yield for the study area. It was about 18 million cubic meter per year. But if the decision makers or policy makers, they want to use for different years, also we estimated for different years. For dry year, it was 14.5, and for normal year, it was 16.3, and also for wet period, it was 36 million cubic meter. And the important part when you the important point when you look at this table, you can see that we have quite large deficit for this study area, for this transboundary aquifer. It is around, you can see here, it is around 42 million cubic meter per year. And when you look at the water balance components, specifically or individually, that you can see here, this one is for outflow through the border, and you can see that we have 32 million cubic meter, that it is really high. And because of this, we have this deficit. And this high outflow, it's because of heavy abstraction that we have in the UAE side, and it makes the gradient steeper, and more water, in fact, is flowing UAE side. And after modeling part, I can say parallel to modeling part, we have conducted also hydrochemical study. And because of that, we sampled 54 locations in different seasons. This map exactly shows the distribution of these wells. These sampled wells that you can see, it is quite shows it's quite covers the whole area. In the when we were sampling the water, we measured some physical and chemical parameters in the on site. Also, all samples were analyzed for the major ions and cations. Based on the and based on the information, based on the results from a hydrochemical study, we figure out that we have 3 main dominant groups. That when the groundwater evolves from carbonate dominance in elevated areas into sodium chloride dominant in plain areas. Also, the chemical composition of most of the samples is controlled by weathering rather than evapotranspiration or evaporation. Through this project, we published several papers that, if you are interested, you can go in publications and find the details. In conclusion, the developed regional groundwater model would help decision makers to have a better understanding of the groundwater budget components. Also, it would assist decision makers to improve existing strategies to enhance the decision making for future developments in different climate conditions. And the most important part also, the research collaboration on shared water resources is key to better development and can be the start for elevating sensitivity of the issue. Thank you so much. And also, this is the beauty of a study area, that at one place you can see different geological units from 286 million years ago till present. Thank you so much. If you have any question, I'll be happy to answer.
Thank you. Thank you very much, Dr. Azizallah Izadi. I guess it's very difficult to abstract such big work and complex modeling in only 15 minutes, but you did that very well. And I suppose there will be some questions. I've seen already a few questions that are addressed to you, and we'll see that at the end of the session. Thank you very much.
Thank you so much. Thank you.
It's time now to go to the next presentation, which will be a presentation by Mr. Ibra Dieng-Gueye. Mr. Gueye is working at the Direction de la Gestion et de la Planification des Ressources en Eau du Sénégal, so the management and planification of water resources in Senegal, and is working with Professor Serini Faye on the following topic: the new isotopic evidence of vertical flow exchange between superficial and the transboundary superficial and groundwater in the transboundary maestration aquifer in the Sénégalo-Mauritanian Basin. Mr. Ibra, c'est à vous. Can you put your mic on? Votre micro. On ne vous entend pas, monsieur Ibra. Voilà.
Oui, voilà, c'est activé. Bonjour, monsieur. Est-ce que vous me recevez? L'écran est partagé.
On voit votre écran, mais vous pouvez peut-être appuyer sur F5 pour faire la présentation. Voilà.
C'est bon. C'est bon. Bonsoir, monsieur Gutiérrez.
Bonsoir, allez-y. Vous pouvez y aller, monsieur Gueye.
Vous me recevez, monsieur Gutiérrez?
On vous reçoit. On vous reçoit.
Bonjour, monsieur Gutiérrez, vous me recevez?
On vous reçoit, mais vous ne nous entendez pas.
Vous m'entendez, monsieur Gutiérrez?
Nous vous entendons. Allez-y.
Est-ce que vous me recevez, monsieur Gutiérrez?
Nous vous recevons tous, mais visiblement, vous ne nous entendez pas.
Je vais faire la... Bon... La raison, je vais procéder à la présentation. La région d'études qui nous intéresse se situe la région d'études s'intéresse à la partie nord du bassin sédimentaire sénégalais, qui se situe à l'extrême ouest du continent africain. Elle couvre une superficie de 40 000 km², limitée au nord et au nord-est par le fleuve Sénégal, à l'ouest par l'océan Atlantique, au sud-est par la région de Matam et au sud par une ligne qui traverse la région naturelle du Ferlo à une latitude de 15°40. Dans cette région, les eaux du Maastrichtien sont marquées par une forte salinité, avec des conductivités qui dépassent souvent les 3000 microsiemens par centimètre. Et du point de vue activité économique, la région polarise plusieurs activités, dont la riziculture et le maraîchage qui s'effectue au niveau du delta du fleuve Sénégal. Comme vous le savez, au Sénégal, l'exploitation des ressources en eau souterraine, particulièrement la nappe du Maastrichtien, constitue un garant pour le développement socio-économique du pays. Ce réservoir qui constitue cet aquifère qui constitue le plus grand réservoir à eau douce du pays est aujourd'hui menacé par une surexploitation qui a entraîné une baisse généralisée des niveaux piézométriques, mais aussi par la présence d'eau saumâtre en profondeur. C'est la raison pour laquelle, pour garantir une durabilité de l'exploitation de ces ressources en eau, il faut impérativement comprendre le fonctionnement du système aquifère, les processus et les zones de recharge, les processus qui gouvernent la minéralisation des eaux et les temps de résidence des eaux. Raison pour laquelle notre objectif de recherche consiste à étudier la relation entre la nappe du maastrichtien et les formations sous-jacentes dans la partie nord du bassin, qui est caractérisée par une surrection de l'aquifère du maastrichtien à travers un dôme sous de minces couches du paléocène, de l'éocène et du continental terminal. Sur le plan climatique, la région d'étude est caractérisée par un climat de type sahélien marqué par une pluviométrie faible et une forte évaporation. Et la saison des pluies s'installe à partir du mois de juin jusqu'au mois d'octobre, avec un maximum pluviométrique qui est souvent atteint à partir du mois d'août. D'ailleurs, les moyennes pluviométriques calculées à la station de Linger donnent une valeur de 417,97 mm par an, à la station de Louga 316,23 mm par an, 262,41 mm par an à la station de Louga et 241,05 mm par an à la station de Podor. Sur le plan hydrographique, le réseau est dominé par la branche principale du fleuve Sénégal, le système du lac de Guerre et les vallées fossiles du Ferlo. Sur le plan géologique, la coupe réalisée à partir des données des forages pétroliers et des données des forages hydrauliques sur une longueur de 280 km à partir du bordure est du bassin jusqu'à l'ouest au niveau de l'océan Atlantique montre clairement la succession des couches lithologiques à partir qui part du maastrichtien, caractérisé par un faciès de sable fin à grossier jusqu'au sable et grès du continental terminal et du quaternaire en passant par les calcaires du paléocène et les marno-calcaires de l'éocène. Cette coupe montre aussi clairement la surrection du dôme de guerre à travers un réseau de failles qui met en position haute ici l'aquifère du maastrichtien sous de minces couches de paléocène et d'éocène. Pour cette étude, au total, 111 échantillons ont été collectés durant plusieurs campagnes entre 2016 et 2021 à travers les missions de suivi de la DGPRE, les projets RAF 7011 et RAF 7019 de l'Agence internationale de l'énergie atomique. La géochimie classique et les outils isotopiques ont été largement mis à contribution pour identifier les processus majeurs qui contrôlent la minéralisation des eaux, les zones de recharge, ainsi que les échanges de flux, les temps de résidence et les mélanges possibles entre les nappes. Ainsi, l'analyse des données hydrochimiques montre une évolution des faciès qui se fait suivant le sens d'écoulement de la nappe. Ces faciès vont du pôle bicarbonaté calcique et magnésien vers le pôle chlorylé sodique en passant par le pôle bicarbonaté sodique qui caractérise les eaux très anciennes ici au milieu. Et parallèlement aussi, on observe une augmentation significative des teneurs en chlorure dans le même sens de l'écoulement de la nappe. La corrélation établie entre les ions sodium et les ions chlorure montre une dissolution de l'halite dans les eaux de la nappe profonde avec un excès de sodium par rapport au chlorure pour les eaux faiblement minéralisées qui pourraient être dues à des échanges de base. Ces échanges matérialisés ici sur ce diagramme montrent que l'échange s'effectue dans le sens de la libération du Na+, et la fixation du Ca. Ces échanges sont évoqués par plusieurs auteurs dans la littérature comme étant un phénomène prépondérant dans la chimie des eaux du maastrichtien. Sur le plan isotopique, Les teneurs en isotopes stables mesurés dans ces eaux montrent que les eaux souterraines ne correspondent pas pour la plupart des points à la signature des précipitations actuelles. Les teneurs sont relativement homogènes avec une absence d'évaporation, ce qui suggère que ces eaux sont probablement rechargées dans des conditions plus humides, que les conditions actuelles. La plupart aussi des points se placent sous la droite météorique mondiale et celle locale, sauf pour quelques points qui se situent au nord et au nord-est de la zone, qui se placent sur la droite météorique mondiale, témoignant d'une recharge très localisée par les eaux de pluie. Les teneurs en tritium mesurées aussi dans la zone montrent globalement que l'activité tritium est très faible dans ces eaux, souvent même inférieure à la limite de détection. Cependant, quelques points ponctuels sont localisés à l'est et à l'ouest de la zone montrent des teneurs comprises entre 2 et 3 unités tritium. Ces fortes teneurs sont probablement dues à un mauvais équipement des ouvrages. L'activité carbone 14 dans ces eaux est relativement faible. Ça varie entre 0,89 et 51,3 ppcm et les teneurs en carbone 13 aussi entre 13,72 et moins 2,04. À l'est de la zone, on a des... À l'est de la zone, à l'est de la zone, dans la région du Firlo, on a des activités qui sont très faibles, généralement inférieures à 2 ppcm avec des teneurs en isotopes appauvris, variant entre moins 6,5 et moins 7,5 vsmol. Ces activités montrent un vieillissement rapide des eaux depuis les bordures vers le centre du bassin. Cependant, la partie nord et aux alentours du lac de Guerre, nous avons noté des activités de carbone 14 plus élevées, 25,63 ppcm à Diaglé, dans le village de Diaglé, et 51,03 à Keur-Mor-Ibra, qui sont probablement dus à une alimentation par les nappes supérieures qui sont à haut saumâtre. Les âges calculés varient entre l'actuel et 35 000 ans. Ces deux points se trouvent sur l'axe du dôme où le toit du Maastrichtien est à moins 100 mètres de profondeur et peut remonter jusqu'à moins 40 mètres aux abords du fleuve. En guise de conclusion, nous pouvons retenir que le bassin sédimentaire sénégalais est marqué par des présences de 3 systèmes aquifères. La surréaction du dôme formée par un jet de faille de direction sud-ouest-nord-ouest confère à l'aquifer du Maastrichtien une position haute à l'est du lac de Guerre entre Dagana et Bokidiawé, où le toit de l'aquifer se situe à 100 mètres de profondeur. Les interactions eau-roche constituent le moteur principal de l'évolution des faciès des eaux. La dissolution des évaporites, à savoir la halite, est à l'origine des concentrations relativement importantes en chlorure et en sodium. Ce phénomène est amplifié par les phénomènes d'échange de base, par les phénomènes dits secondaires qui sont mis en évidence par les processus d'échange de base. Les teneurs en isotopes stables très appauvris montrent la présence d'eau très ancienne, probablement rechargée dans des conditions plus humides. Cette paléo-recharge est confirmée par les données de carbone 14 qui montrent des activités à l'est du lac de Guerre, dans la zone du dôme. Le carbone 14 montre des activités relativement importantes, parfois supérieures à 25 ppcm, qui suppose l'existence de phénomènes de mélange avec des sources plus récentes. Comme perspective, on retient que suivant le modèle d'écoulement, il sera intéressant dans la suite de nos travaux d'utiliser des radiochronomètres à longue durée, comme le krypton, qui constitue les prochaines étapes de nos travaux de thèse. Merci pour votre attention. Je vous remercie.
Merci beaucoup, Monsieur Ibra Diangueye. En français. Je ne sais pas si vous avez la possibilité de nous entendre. J'espère que le son reviendra chez vous pour les questions. Thank you very much for this presentation that showed evidence of mixing of water proved by the use of isotopes and geochemical analysis. It's really an interesting component of the methods that can be used in transboundary aquifers. Now we are going to move to shorter presentations. Short presentations which will be done first by Dr. Kassem Natouf from Damascus University. He's a groundwater specialist from Syria, and he will have a talk about the role of the groundwater divides in transboundary aquifer. Mr. Natouf, Dr. Natouf, are you here? Are you able to present something? Dr. Kassem Natouf. So it seems that Dr. Kassem Natouf has some difficulties to connect. Then I suggest we pass to the next presentation, and if we manage to connect, we come back to him. The next one is from Professor Zoran Stevanovic, professor in hydrogeology at the University of Belgrade in Serbia, that we already know. Professor Stevanovic participated yesterday to panel 6 on the transboundary aquifer experiences across the world. Good morning, Professor. You will talk today about the needs related to sustainable transboundary water management of the sensitive and complex karst aquifer system of the Prespa Ohrid. I don't know if I'm pronouncing well. It's between Albania and former Yugoslavian countries, I guess.
Thank you very much, Mr. Gutierrez. But according to the program and what our understanding, this short presentation should be broadcast. It means that we already recorded this 5 minutes.
Exactly. Thank you for being there. You will be able to answer the questions after.
Yes, of course. Yes, of course. Ladies and gentlemen, dear colleagues, it is my pleasure to present you an article, Needs Related to Sustainable Transboundary Water Management of the Sensitive and Complex Karst Aquifer System of the Prespa Ohrid Lakes, which is shared between Albania, North Macedonia, and Greece. My name is Zoran Stevanovic. I am one of the authors. Our team is led by Romeo Eftimi from Albania and also is contributed by Vasko Stojov from Hydrometeorological Survey of North Macedonia. The Ohrid and Prespa lakes are situated in the southeastern Europe, in the Balkans Peninsula, and they are included in a UNESCO World Heritage List in 1971 due to very rich biodiversity. There are rare and endemic representative of flora and fauna, and some of them are included in a IUCN World Rare List of the threatened species. The study area is characterized by complex geology and hydrogeology settings. There are high mountains, Malitate Galičica, in between the two lakes, consist of the thick and bedded and massive limestone of Upper Triassic and Lower Jurassic age. The limestones are highly karstified and thickness may reach more than 500 meters. The connection between the two lakes are proven by the tracing test, and the water from the Zaver swallow hole, Ponor, on the Prespa Lake side, has appeared on the two springs, Sennaum and the Tushimir spring in Northern Macedonia and Albania respectively, within only 6 hours, which has proven an apparent high velocity of 0.81 meter per second, which is one of the highest recorded in southeastern Europe. The measurements of the Prespa Lake level between 1950 and 1985 has found no any significant change. That water level was mostly stable. But since 1985, there are considerable decrease of the water level. We may even say that is catastrophic. And currently, an altitude extreme is a 9 meter between that before 1985 and current one. The causes are many, but the precipitation rate are slightly decreased, while evapotranspiration rate and air temperature during that period were not so significantly increased. Possible causes of the Prespa Lake level decreases we group in 3 categories. The first are geological tectonic factors, for example, widening of a karst conduit during a long period of time, and the washing of channels and the karstic conduits. The second are anthropogenic reasons, intensive use of lake water for irrigation and the drilling of the wells in surrounding area. And the third group are effects of the climate change, the factor which is not commonly considered by most researchers till now. In one of the analyses, our colleague Stoyov concluded that there are some annual deficit of about 50 million cubic meter of water per year, which converted into discharge result with a deficit of 1.7 cubic meter per second, or decrease of 20 centimeters, which is somehow comparable with existing situation. Finally, the lowering of the level of lake has exposed one old dam-like construction around the Zaver Ponor on the Prespa Lake side. This construction probably dated back to the Roman time and proves that in the past there were some certain periods of hotter climate, and the cyclical character of the climate condition is very probable. To conclude, that climate variations and non-effective management of the water resources could be the main reasons for this lake level decrease. And the proposal from our side is to establish a joint consultative water management body and sharing information, and also establish one international water monitoring network, because now many data of water utilization are missing, and the proper monitoring which be an important step towards the sustainable water management and prevention of the further deterioration of the lake. Thank you for your attention.
Thank you for this video, and which shows again that monitoring is necessary to understand and validate hypotheses. We can now go to the talk of Mr. Kassem Natouf. We was able to speak about the role of groundwater divide in transboundary aquifers, if the connection is good now. Dr. Natouf?
Yes, hello. Do you hear me and see my screen, please?
We hear you and we see part of your screen, yes.
Hello, everybody. My name is Kassem Natouf. I will speak about the role of groundwater divide in transboundary aquifer. My presentation is addressed to people who are not familiar in details in hydrogeology. So I have to apologize from experienced hydrogeologists that because they will find it simple. But however, I will proceed on.
It's okay, Mr. Nattouf, but please keep the time which was
Yes,
previewed
okay.
of not more than 5 minutes.
Okay, I will clarify the following ideas: hydrogeological concept of groundwater divide, the necessary data to determine the path of groundwater divide, methods of drawing and delineating the groundwater divide, indicate the geological and hydrogeological factors affecting the location of groundwater divide, and what is the significance of groundwater divide in transboundary aquifers. What is a groundwater divide? Here, if we have the land surface here, where we have some forests and some farming. Also, we have the groundwater table before infiltration. So after we have rainfall, and then we will, and irrigation, and then we will have infiltration from irrigation and also infiltration from rainfall. And here we will have a dome in the groundwater table, and here a groundwater divide will will form, and the groundwater will move in different directions, in this direction and in this direction. And here we will have this divide, and it is considered as no flow boundary. What is groundwater divide? So the definition is groundwater divide connects the higher points of groundwater table in a free aquifer or basometric table in confined aquifer. This line represents a vertical boundary through which groundwater does not flow, so it is classified as a no flow boundary. Typical groundwater divide, considering the unconfined aquifer between two rivers connected to the aquifer through their beds, and the water table is subject to infiltration. It is proved mathematically that the groundwater divide may be formed, and the distance from the origin and the height of the groundwater divide can be calculated. In more complex conditions, where the formation of groundwater is affected by a big number of factors, the groundwater contour map can be used to prove the formation of groundwater divide. In this case, we might have a simple karst aquifer where maybe several groundwater basins with minimal hydraulic connection, each drainage to a different spring or set of springs. The limits of each basin can be considered as a groundwater divide and determined or by mapping basometric contours and thus establishing regions of divergence to flow, or by water tracing, perhaps using fluorescent dyes or isotopes. What is the significance of groundwater divide in transboundary aquifer? If we have two countries, country A and country B, and we have this transboundary aquifer between the two countries, and according to groundwater level contour map, here we have a groundwater divide. In this case, the country A will consider this part of the aquifer as interior part of the aquifer for country A. And the actual transboundary aquifer will be considered only this part. What data we need to draw or to define the groundwater divide? Groundwater contour map is based on data describing the subsurface hydrogeological structure, in particular the extension of the aquifer. The groundwater level is in a number of monitoring wells, which is calculated from the depth of groundwater above the reference level. Methods used to draw groundwater level contour map. Several methods are used to map the water level, including creaking, inverse distance, curvature, and others. All of these methods use special statistics to find general trend in the changes of groundwater level in relation to coordinates of its measurements, that means points or wells. On contour map, the directions of groundwater movement are determined perpendicular to the isolines and to lithological changes, and then the groundwater divide passes along the path in which the groundwater moves in different directions. Factors affecting the location of groundwater divide. The location of groundwater divide is affected by seasonal intensity of groundwater recharge. The pumping from the groundwater pumping will lead to increase in groundwater movement speed and change in directions of movement, and thus the shape of the dome will change along and the groundwater divide will be formed. Also, lithological characteristics of the aquifer.
It's time for the conclusion.
We have an example, the Nubian aquifer system. The Nubian aquifer system extends over a vast area in Egypt, Libya, Sudan, Chad. The western boundary of this aquifer is a groundwater divide extending from Tibesti Mountains to south north and to northwards. And thank you for your attention. And that's all. Thank you.
Thank you for keeping the time, and thank you for this useful reminding about what is the groundwater divide. Not forgetting that groundwater divides can also move. They are sometimes not fixed in the geology and geography. It's time to go to the final presentation, if I'm not mistaken. This will be a video from Mr. Yusuf Al-Mouji. I don't know if Dr. Al-Mouji is here to answer the questions afterwards. Here is the video.
Hello everyone, my name is Yusuf Al-Mouji. The aim of this presentation is to show evidence for an ongoing northward movement of the intertropical zone due to climate change that will bring more rains to southern Arabia and enhance the sustainable management of the extensive transboundary aquifer systems in the region. This movement is well documented in the literature, and the most recent study indicates a zonally opposing response of the ITCZ with a northward shift over Eastern Africa and the Indian Ocean and a southward shift in the Eastern Pacific and Atlantic Ocean by the year 2100. This slide shows how convective cloud development is currently prevented by a temperature inversion located over the region, while a northward shift of the ITCZ would lift the height of the temperature inversion, leading to stronger convective cloud development and higher monsoon rainfall like it happened about 7,000 years ago. A northward shift of the ITCZ will increase both the northeast winter and the southwest summer monsoon seasons and enhance recharge to the extensive transboundary aquifer systems, but also increase the occurrence of heavy flash floods that can cause considerable damage and heavy losses of human lives. Hence, adopting a water resources management strategy for enhancing recharge of the aquifer systems and across the peninsula, while minimizing the damaging effect of the flash floods at the same time, is recommended through building recharge dams and flood conveyance systems near the outcrop areas of the aquifer systems in the catchment zones. Thank you for your attention.
Thank you, Dr. Yusuf. And now it's time to ask the questions that you have already written in the Q&A box, and I will try to read the questions and ask our panelists to answer them. Some questions are very general. The first question is addressed to every speaker. How do you plan to restore aquifers with river water or rainwater? I don't know who would like to answer that. Any volunteer?
Dr. Alexis?
Yes.
Yes, the question is too general, as you mentioned, but probably we can use aquifer managed recharge to restore the aquifer. It is only the way that if we want to use river water, or we can say rainwater. Rainwater, it means runoff. And we can use the runoff as managed aquifer recharge for artificial recharge, and then during the time for the probably few next 5 years or maybe 3 years, we can be optimistic that the aquifer, some parts will be restored. This is my understanding from the question. I mean, it will be very general.
Yes, it is true. It's very general. We also have some programs of removing the impermeabilization of soil in Europe, in France in particular. Several towns are now considering that having roads and very impervious surfaces on soil prevents water to re-infiltrate and recharge the groundwater bodies. So that's also some directions. There is also in the rural zones the possibility to facilitate the infiltration at large scale by having some, for instance, the plowing perpendicular to the runoff and things like that. But it's, as you said, as you mentioned, a very large question that probably does not find a unique answer. Let's go to the next question. What are the available software for mapping of transboundary aquifers? It's a question that I have already seen in the conference, and it's also a very, very large question. Probably it can also be merged with another question, which is how to quantify the flow of transboundary groundwater. The next one. Probably, Mr. Azizallah, I can give you the floor again to answer this question, because one of the answer was clearly shown in your presentation.
Thank you, Dr. Alexis. To quantify the flow of transboundary groundwater, definitely we need monitoring network. If we have monitoring network, it means we will have groundwater level, and then based on this data, we will have some interpolation methods, and then from that we can interpret that the flow will be from which direction to which direction. But for mapping the transboundary aquifers, honestly, I have no answer. It can be with, I think, with through the big institutions like UNESCO, like this. I don't know really.
Yeah, I think the question was more about which tool, which software, which mathematical tool could be used. Professor Stevanovic?
It is, these two questions are too general, really. And we highlighted many times that it is not so easy that things can be done like this and just put in the hands of the water managers and decision makers to do the rest. we at our university, we are teaching the students for 4 years how to make a study in hydrogeology and how to do this proper technical job. If you ask me what exactly software we can use, you need a field mapping. This is essential thing. And then you can use the software as a GIS tools to make everything in a let's say, digitalize everything, every map, and to make a database and to collect the information. And this can be later used as a managerial tool. But you cannot map from your office. That's very clear. Even if you have a geological map, you need a field research, you need field testing, you need a tracing test. Yesterday I have just presented, and in today's presentation you heard that sometimes you have a very large apparent velocity, then you have a groundwater pattern and movement in the different directions. So you really need a proper study in order to create the base for, let's say, something which is management and the decision-making and the equitable share of the water. Many times we repeat the same. You cannot talk about equitable share if you don't know, if you don't know the aquifer system, and if you not quantify the available resource. So it's mean this second question, how to quantify flow. You need a proper field test, you need a tracing test, and many, many things before you can reach to the conclusion how the water and, as you mentioned also, groundwater divide is changed versus the time. So maybe I was a little bit long, maybe more academically speaking, but this is simple that we like to warn our colleagues who are not professionals in technical matters that they should closely cooperate with a hydrogeologist in the field and then create the base for the rest. Thank you.
Thank you for this sound answer. We are coming back to Dr. Azizallah Izzadi with the next questions, set of questions actually. This presentation raised a lot of interrogations. One of the questions is about the software you used for modeling. Is it ModFlow? And can you answer to that already?
Yeah, it was ModFlow, and I mentioned in my, I think, presentation. Yes, it was ModFlow.
Thank you. Another question from Professor Larabi. Thank you for your presentation on Oman aquifer. Based on the piezometric map, it seems that the aquifer is not much exploited, but seems to discharge more at the west boundary. Indeed, is this boundary that you have to investigate more in order to give to your model more accuracy? Yeah, it's also a question that I had myself. The boundary of your model is the boundary of the nation as well. So you fixed the boundary on the administrative boundary by fixing the potentials, no? The heads. And so you did that by changing the potential at each time step to show the decrease of the water level? How did you do?
Yeah, we had quite enough observation well in the border, and for the study area, we investigated maybe several interpolation methods, and we understood that Bayesian encouraging method is the best method for the study area. From that rasters, and also with the help of GIS tools, we extracted data for the border, and we used that data as a head for the boundary.
Thank you. Thank you. The final question, which is written here. The recharge area, which was delineated based on water table fluctuation, I wonder, is pre- and post-monsoon condition, which has been observed for that. It's a question from Ragwendra Pratap Singh. Is it addressed to you as well, Mr. Izzadi, I suppose?
Yes. Through that water table fluctuation method, in that study, specifically, we combined water table fluctuation and also water balance methods together, and we considered all water balance components. And also, it was for long period. It means from 1996 to 2013, and among this time, definitely the monsoon is considered. I mean, it was a historical time, and we had the rainfall for the monsoon and for non-monsoon times. Yes, it is considered.
Okay. Mr. Larabi says, okay, but this boundary is changing with time.
Yeah, we considered the time varying boundary condition. We didn't consider the fixed head for the boundary. We considered the time varying, and in fact, I can say monthly time varying condition for the boundary.
Okay, yes, that's what I understood too. Thank you very much. Next question is, what's in the future? How do you extrapolate in the future?
Yeah, it is a very tricky question. This one is, I understand it will be very difficult, and we will have, based on different scenarios that we have in mind, maybe we can use, different methods such as, I don't know, just simple regressions, maybe, or more complicated methods like ANNs to just extend this data. But I know, but it is very difficult. It is very difficult, and it needs more efforts.
Thank you for all those details. Maybe other questions regarding other speakers? Or other speakers can also ask questions if they want to take the floor for that. Okay, myself, I have a question for Samuel, if he's still here. I would like to know a few things regarding his presentation, his basin. There is something I didn't quite understand in the western boundary of your basin when you showed the groundwater flow with arrows. The arrows are converging towards the boundary, whereas I would expect that the boundary is like a groundwater divide, as Mr. Natuf has shown, and then the arrow should be classically in the other direction.
Hello. Okay, thanks, Alexis. Actually, it's only that my internet is now very unstable. It's at the western boundary. What is actually happening is that you have got a flow coming from the west, and it's actually moving towards, it's like converging towards the Makhalkhali Pans.
Okay.
Yeah.
So it's
and then
both,
I have the question. Sorry?
It's both surface water and groundwater flow directions, which was maybe drawn.
Yeah, you're right. Yeah.
Okay. The other question that I have on your presentation regards the mining activity. You showed that the mining activity is, if I remember well, 63% of the water use, of the groundwater use, so it's huge. How does it impact the quality of the water and also the quantity aspects?
Yeah, actually, as I pointed out during the presentation, in terms of quantities now, we have got a growing population within the basin, and the demand for water is actually increasing. But in terms of the supply side, it's actually fixed, and in some instances, it's actually deteriorating because with the mining, you get intrusion of the saline water. So it's actually having an effect on the available potable water. So we have got a huge challenge, and this is why we're saying we have to find a way of optimizing the available resources so that we can actually stretch whatever we have at the moment.
Okay, yeah, I suspected that, of course. Any more questions?
If I can ask a question.
Sorry?
Alexis, I just wanted to take the opportunity that I have the floor. If I could ask Lucia, actually, there was a presentation on the mixing of groundwater, and I just wanted the clarity if she could bring up the slide.
Sure. Hold on. Let me try if I can figure out which slide, the quantification.
Hello? Can you hear me?
I can hear you. Can you hear me?
Hello?
Can you hear me? Alexis, can you hear me?
I can hear you both.
Okay.
So, Samuel, is it the slide that you wanted to see? I think we are losing Samuel, probably a problem of connection.
Oh, I didn't get the question, so I don't know how to answer.
Question was relative to the mixing of aquifers, but
yes. I mean, I can explain this again if that is useful, or shall I just wait to see if he comes back?
He disappeared, so he probably will come back. Okay. Regarding the mixing of aquifers, I had this question as well for Ibra, sure. But you can also participate to the answer. When you have a mixing of aquifers evidenced by isotopes or geochemical interpretation, how are you sure that it's not coming from the point where you are selecting the sample? Because many wells, I mean, particularly in the Maastrichtian aquifer, are not really isolated from the surface, from the top aquifers. So you may have a mixing which is very punctual, very local. How can you make the difference between a global mixing of aquifers and a very local one in a well?
Well, in our case, in this study area, we were looking at 45 boreholes of different depths, and all of them were actually active pumping boreholes, and we've seen that these mixtures, not only in one of them, but in plenty, most of them have these mixtures. And in the ones there, the faulted areas that actually in this region is that facilitating the outflows through the regional faults for the tectonics, we see that is actually helping this flow going up, and we see at different depths, not only in one specific borehole, but in plenty boreholes in the same area. So that's how we.
It makes sense. Mr. Ibra, maybe you want to add some words about that? Vous voulez dire un mot sur le mélange?
Oui, Monsieur Gutiérrez. Nous, dans le cadre de notre étude, on a fait notre mieux pour essayer de trouver les logs des forages et s'assurer que ces forages-là les nappes sont isolées dans le cadre de l'échantillonnage qu'on a effectué en 2021. Et c'est pourquoi on pense que ces eaux-là sont typiques du Maastrichtien. Les eaux qu'on a échantillonnées sont typiques du Maastrichtien. Et ce que vous avez dit aussi, c'est possible dans la zone. Il peut y avoir que les forages ne soient pas bien isolés. Et du coup, il y a un mélange entre les aquifères supérieurs et ça devient, et la valeur qu'on mesure devient donc ponctuelle.
Merci. Thank you. Okay, Sam, you wanted to ask your question if you are reconnected. Samuel, we didn't get your question, so if you want to ask it again. No more question.
Yes, sorry. I want to ask Mr. Zoram, please. I know that he is hydrogeologist specialized in karst aquifers. I even attended his workshops, about 7 days workshops, about a few months ago about karst aquifer. I would like to know if he has any experience in aquifer in Arab region, in east coastal of Mediterranean, or if he can give us some example or information about that. It will be very kind of him, please.
Your microphone is off.
Yeah. Thank you very much, Mr. Qasim, for this raising this issue. So from the 2014, we traditionally organized the 7 days free of charge course with support of UNESCO in the two countries, in Bosnia and Herzegovina and in Montenegro. And up to now, we have more than 100 participants, means every year about 20. So you are welcome, and all of your friends, colleagues are welcome. If you ask me about the experience in the Middle East, I personally, yes, I have. I worked for the UN for 3 years in the Middle East, in Iraq, and we did a great study in exactly on the karst aquifer, the monograph about the hydrogeology of this region of the Zagros and Taurids mountains are available in FAO organization and is also delivered free of charge to everybody who will be interested about. So there are plenty of karst studies along the Mediterranean coast. There is also a large project which is currently ongoing where the Tunisia, Lebanon are involved together with some European, South European countries, French, and Germany is coordinating. This is the Karma project. And if you type just the Karma on the internet, you will find some more information, including the Mediterranean karst map, which is now going to be prepared under frame of this project. So, however, you will have opportunity maybe to discuss, not to boring other people, but I can share with you whatever would you like. Thank you for interest.
Thank you. Thank you.
Well, thank you, everybody. It's almost time to close this session, so we will conclude. I remind you that everyone can continue asking questions to speakers or to each other through the WUVA application. So feel free to share your questions and answers. Thanks for all these very nice, interesting presentations in this session. We're looking forward to more sessions like that. I will now ask Rita to end the session. Thank you very much.
Thank you, everyone. I would like to thank all the speakers for these very interesting presentations. We learned a lot about the more technical aspects of the modeling of aquifers. The session now will have we will have a 15-minute break, and we'll come back at 12:30 Paris time for the next session. It will be session 17 on the advances in the assessment and mapping of TBAs. So after a short break, hope to see you all around, and thank you for joining us today. Thank you.
to have it on full screen. Can you have presentation mode?
Is it okay now?
But can you try to move the slides now?
Yes. Do you move?
Right now? No, it's not moving. No, it's not moving. Can you stop sharing and resharing, please? And maybe have the presentation on full screen mode before you share. So stop sharing and then have full screen mode for the PowerPoint and then share the full screen one. Yes, now have the PowerPoint in full screen.
Okay, I will try the full
screen first and then share the full screen mode. It will be PowerPoint with a lighter red color in full screen mode when you select it from the Zoom opened applications.
Share screen. Okay.
Okay, try to have it on a full screen now.
Okay. It's now.
Yes. Now can you move? Yes, it's moving.
Okay.
Thank you.
I'm sorry. This is the map of
perfect.
Groundwater bodies in Bulgaria and Serbia, and this is the groundwater near the border. Okay, I will. Okay, I'll start from this. Sorry. For better visualization, a schematic profile from south to north has been prepared, facilitating the analysis of the available information. The first step to clarify the factor influencing the formation and movement of groundwater. Geological conditions predetermine the presence of different types of groundwater. Along the state border, the most widespread are the fractured aquifers water, formed mainly in the weathering zone of magmatic, metamorphic, and sedimentary terraneous and terraneous carbonate rocks, about 87% of the total length of the border. Here is a diagram of percentage distribution according to collector type along the border. Different types of aquifer system have also been studied. The first type include alluvial deposit of Timok River, which is in the northwestern part of the state border. Here, the state border coincides with Timok River. An unconfined aquifer has been formed in the terrace on the river on the both sides on the border, and the water are directed toward the river. This means that transboundary groundwater transport is not possible. The second type aquifer are in places when the border crosses the terraces of some smaller river, with not very large or often interrupted terraces. Due to the mountainous nature of the relief, their terraces are of relatively little importance. The waters formed in them, in most cases, are with small water quantities, and they move parallel to the river when crossing the state border. In the slopes of the valley, fractured aquifers water are formed, and the direction of their movement is perpendicular to the riverbed, and there is no cross-border transmission also. When the border passed through a karst area, the typical karst aquifer have a relatively small distribution along the surveyed border area. Some of them form parts of clearly defined karst basins, linearly extend in the east-west directions, and having important hydrogeological significance. Such are the cross-border karst basin in the southern slopes of the Balkan Mountains, with predominant water flow through canal gallery network. According to our previous research, the geomorphological and hydrogeological conditions in separate sections of this area create a probability for groundwater flow from Bulgaria to Serbia and from Serbia to Bulgaria. Other types of karst collectors are isolated tectonic blocks with small areas bordered by non-karstic rocks. They are characterized by development of typical mountain karst, mountain type of karst, and are located south of Nishava River, which crosses the border. Sarmatian sediments form a layer complex with well-defined aquifers in it, attached to sands and limestones in the northern part of the border here. In this stage, it is not clear whether they are transboundary water transfer in this aquifer. This needs to be determined in the near future due to the importance of this aquifer for water supply to settlements on both sides of the boundary and anthropogenic pressure for agriculture. This is some example. When border crosses along a watershed, groundwater has formed in a fracture in weathering zone of the rocks. In this case, the surface watershed along which the state border crosses coincide with the underground one. The formed groundwater flows from the ridge to the territory of respectively country, and there is no groundwater transfer. The analysis of the factors proves that during most of the border between Bulgaria and Serbia, the probability of cross-border transmission is insignificant. This is due to the wide distribution of fractured aquifers groundwater in the weathering zone of the rocks, whose direction of movement coincides with the slope of the terrain, and the fact that the most part, about 82 of the state border, passes along the watershed. Here is one diagram with a percentage of the factors of direction, movement of groundwater. There is a possibility for such a transfer only for the karst basin and for the Sarmatian complex, but this at this stage is not sufficiently clarified. Only for the well-developed dominantly cavity karst system in the Western Balkans, the presence of transboundary groundwater transfers has been established. The obtained results allow to locate although not very large areas of the state border between Bulgaria and Serbia, in which future research should be directed. An important steps in this regard will be the systematization of existing hydrogeological information for both sides of the state border in a single database. It will be used for future GIS analysis and model solutions, which would allow to look for an opportunity to unite some boundary groundwater bodies into common transboundary ones. This would significantly help the overall protection of water resources and their joint management by the two countries. Thank you for your attention.
Yes, thank you so much, Boyka, and you were sharp on the time allowed to you, regardless of the time we lost in interrupting you. Thank you so much.
I'm sorry.
No, that's okay. I highly appreciate it. And this is very interesting discovering, so to speak, at least for me, where you actually don't have a transfer, and this coincidence of the border being aligned along the watersheds, is really of interest. However, as you clearly pointed out, you still do not know for sure about the karst system that lies underneath some places and that may or may not cross the border. So, if I understand you correctly, this is the case of future research on defining karst groundwater.
Yes, and especially for the Sarmatian aquifer in the northern part of the border.
Thank you so much. We might have some questions at the end, so I'm just advancing myself too much here. Thank you again.
Okay. Thank you.
All right, we'll move on with the next speaker, Mikhail Brenshich. I hope I pronounced your name correctly, Mikhail.
Okay.
Thank you.
It's okay.
Mikhail is a professor at the University of Ljubljana, and he will be speaking today on the Karavanke Karavanken transboundary groundwater body between the republics of Austria and Slovenia, not far on this part of the world.
Yes.
The floor is yours. Thank you so much.
Yeah. Can the lady before stop sharing the screen, because otherwise I cannot share mine?
I think it's possible.
Okay, I will start now. Share.
Okay.
Okay, do you see my presentation? Yes, okay. Good afternoon to everybody. And today I will try to represent our common work with the Austrian colleagues. I'm coming from a small, teeny country from the Central Europe. And we have a lot of karstic rocks. Nearly half of the country is covered by karst. And I think that you, as a hydrogeologist, you very well know this. But I will show today not the typical karst, which is usually in the southern part of the country, but I will talk about the karst on the boundary between the republics of Austria and Slovenia. And so this area is also so-called transboundary groundwater body, according to the Water Framework Directive we have in Europe. I would like to acknowledge also my co-authors coming from various institutions, Walter Poltnik and Johann Schlamberger from Austria, and colleague Stojan Kranz from our Directorate for Water. So what I will talk today, I will talk a little bit about the geographical description, so to have an idea where we are. Then I will try to explain why we start this work. What was the raison d'être for this work? Why we start this? Then I will try to explain how the cooperation framework works. And of course, something about methodology, results, and at the end about the conclusions. So where we are in the border region between the Republic of Austria and the Republic in Slovenia, which is in the south. So we are now in the Central Europe. Here is Italy, and this is so-called Adriatic Sea. And so that's the area we have investigated. In the north, it's Austria, as I said, and the south is our country, Slovenia, and that this hatched area is the area we have performed various investigations. And of course, at the end, we established so-called transboundary groundwater body. This is area which is mountainous area. It is, according to Alpine standards in the Central Europe, relatively high. Mountains are over 2,000 meters. And it is interesting that here we have very long mountainous regions, which are cut by narrow and long valleys. This is in general geography, and you can see here the impression from the area. And how we start this work. It is long ago that was established that some transboundary groundwater body exists and so on. But only recently, let's say in last 20, 30 years, people starts to think about the importance of this transboundary water flow and so on and so on. And as you maybe know, in the past exists a state which called Yugoslavia. And in this state, they start to drill a long road tunnel between Austria and what is now Slovenia. And this rock tunnel was 8 kilometers long. And this road tunnel crossed various important aquifers. And as a consequence of this drilling, in the tunnel appears many important springs. One of the springs, it has nearly 200 liters per second. So these are really big springs. And at that time, authorities established that it would be nice to know from where this water is coming, because it was potential water supply for various cities around. And that how starts the cooperation with Slovenia and Austria, in the sense that they try to establish the common recharge areas of their springs. And so we first start to work in the area of the tunnel, and we perform very detailed geological and hydrogeological work. There is a result of this work. And what is also important, both countries established so-called bilateral commission between Slovenia and Austria. And usually in Europe, the neighboring countries, they have so-called water commissions, joint water commissions, where they are talking, discussing, managing, and so on about the transboundary water issues. But usually these transboundary water issues are related to surface water. Nobody, or at the start, nobody cares about groundwater. So therefore, they establish sub-commission inside of this so-called DRAWA or DRAW Commission in German. And this was so-called Commission Drinking Water Reserves in Karawanke. This is the mountain ridge. And this commission or this sub-commission was responsible for coordinating this work. And how we start? This mountain ridge is relatively long. It is approximately 130 kilometers. And we start first on the west, and then with the separate sections, we proceed to the east. And based on this, we established very detailed database. And this database was a basis for water management for the region. And not only for the water management, but here, as you maybe know, mountains, especially if they are carbonated, or they are carbonates or karst, are very often very important water resources. So there are many springs which are used for water supply. And if we have a spring for water supply, we have to protect this spring. And so therefore we start. So how we work? It was bilateral expert work. So we work in the area simultaneously. Each geologist or hydrogeologist from state work on their own site. And we start with very detailed geological mapping. We re-ambulate, so we correct present maps, but we really worked in a large scale. So it means that it was very detailed work. And what was interesting, that in the areas where were disagreements about geological maps, we mapped this jointly. So it means that we jointly went to the field and discussed and solved the geological problems. The next step, of course, is also hydrogeology. So we performed very, very detailed spring mapping, and this mapping was performed in scale 1 to 10,000, and even sometimes even in 1 to 5,000. At the same time, we performed discharge measurements. We made also simultaneous sampling at important springs. And of course, at the end, we performed joint hydrogeological interpretation. And there is a result. This is a result of the joint geological map. What you see here is generalized geological map. In fact, we also prepared the geological map in very detailed scale. Unfortunately, sorry, it's legend is in German and in Slovenian. And then based on this work, we construct also hydrogeological map. This is hydrogeological map for the whole region from west to east along the boundary. And of course, I have no time to go in details. We were also able to establish cross-border groundwater flow. But not only that, but we were also able sometimes to perform also cross-border tracing experiments. And at the end, what was the goal? We arrived to vulnerability maps. And these vulnerability maps, they were constructed not just for one side of the state border, but it was constructed for cross-border. So it means that hydrogeologists working on the project agree about the vulnerability of the area. And so you can see here the case. There is a state boundary with this dotted black line. And you can see that this vulnerability map is really cross-border map. And finally, we arrived to the agreement. What is the shape of our transboundary water body? And not only this, you can see this in this pale blue color. This is transboundary water body, but inside of this transboundary body, we were able also to determine transboundary aquifers. So it means that we have a body, because it is related also to Water Framework Directive and all these propositions which are defined. But especially inside, we defined 5 karstic transboundary water bodies. So you can see the figure, how it looks like. And this is now the starting point for the common management of this transwater body. And also, we are now currently working also on the issues of the protecting particular important springs. So, going to the conclusions, I think that this is very important step forward. Science was there very important. It was used for the communication between states, and it is important that we learn about a lot about each other. So there was a lot of knowledge transfer, which was otherwise not possible. And of course, there was also many improvements in the management practices, because waterworks, people working on the area, they start to communicate within each other transboundary. And also, we are now discussing how to protect all these springs. So we had, or we still have it, cooperation at different levels, professional, so it means among hydrogeologists and geologists. We have cooperation between water management people. Political cooperation, it is also important because water is somehow opening the doors. And of course, this is also very important. This is important for the general public. So thank you very much. As you can imagine, this was a long project, nearly 20 years, and there were involved many founding agencies, ministries, and of course, also institutes. Thank you very much.
Michael, thank you so very much to you for two things. First, for keeping the time. You're really under the allocated time. That's quite good. And second, this is for telling us about this story. It's an extremely nice case study of cooperation at many levels. And it's not very easy to see this, both scientific, and I was surprised that you also have political cooperation. We have to learn from that. I do not know about the full scale, whether you will go the whole country or just that part, but we will see in some of the questions later. It is indeed a nice case. And I myself will have a question at the end when we come to the Q&A.
Okay,
thank you again, Michael. Thank you.
Thank you very much.
Right. So we are really good in time now. We will have the third speaker or oral presentation here, Jalal Halvani. Oh, I see that he is connected. Thank you so much. From the Lebanese University, he is the director of Water and Environmental Laboratory. Mr. Halvani will speak on the characteristics of groundwater in the Hasbani River in Lebanon. And again, you have up to 15 minutes. And if you go over 14, I'll tell you that you have 1 minute left to wrap. The floor is yours.
Thank you, Mr. President. Good morning, all colleagues. I will present it to you a short presentation concerning the characteristics of groundwater in the Hasbani River in Lebanon. The Hasbani River is one major tributary of the Jordan River. As you can see on this map, this is the Jordan River between Syria, Jordan, and Lebanon and Palestine. The Hasbani River runs for 40 kilometers in Lebanon before crossing the border to join with the Banyas and Lidan rivers from Syria and form together the upper Jordan River. In the Hasbani Basin area, the population does not have access to collective drinking water supply system, and water that's supplied by the use of groundwater. Almost every municipality has a private well to meet people's water needs. Hence, our study of groundwater quality is an essential tool for better management of water resources in the area. Indeed, groundwater chemistry is very important in determining its possible usage. The hydrochemical studies at regional scale are an important tool for water management plans, and we can find there are no previous articles on the hydrochemistry, geochemistry, or the quality of groundwater in the study area in reason of the political situation in this area. The objective of our work is to study the geochemistry of the Hasbani Basin aquifers. And the aim is threefold. First one, determine and understand the hydrochemical characteristics of the Hasbani Basin's groundwater. Second, determine the geochemical processes that contribute to these characteristics. And the third, locate any possible source of pollution. Our study area, this is Lebanon, and we are here. So we are here in the south. This is Syria. This is the Hermon Mount, the highest mountain in South Lebanon. Our study is located in southeastern part of the country, about 100 kilometers from Beirut. It has an elongated oval shape of northeast, southwest direction. It lies at the Lebanese international boundaries with the Syrian territories to the east and the occupied Palestine to the south. With an area of 670 square kilometers, it formed about 6% of the total area of the country. For our study, 30 groundwater samples were collected from the 3 aquifers of the study area. From a geomorphological viewpoint, the basin can be subdivided into 4 main parts. First one, what we call the elevated areas. Its altitude from 1,350 to 2,080. This is Harmoon mountain. This area is characterized with the slopes exceeding 30 degrees. It constitutes 32% of the whole basin. Gentle slopes with from 800 to 1,350 meter altitude. This area is characterized with the slopes varying from 10 to 25 degrees. It occupies around 42% of the total study area and embrace most of the basin village. And the third, as we call the plateau, altitude from 500 to 800 meters. It represents around 19% of the total basin area and has the slopes ranging from 0 to 5 degrees. And the last one, it is the plain, altitude 200 to 500. It constitutes the lower part of the basin with the slopes inferior to 2 degrees and occupied around 7% of the study area. The area is characterized by a typical Mediterranean climate with wet winters and hot and dry summers. The precipitation occurs during only 7 months of the year, in the period between October and April. And the amount of precipitation varies across the catchment from 600 millimeters per year in the lower part to 1,100 millimeters per year over the elevated area. In how we have sometimes snow at high altitude. The basin is rural with only 4% of urban area. Its main economic activity is agriculture, with about 27% of the basin area covered with agriculture land. Next. Sorry. Okay. Concerning the geology of the area, As you can see, the major geological outcrop in the basin, it's the Jurassic. It covers 51.5% of the basin area. The oldest rocks observed in the basin area are the lower Jurassic, G2 to G3. It's found on the small patches in Mount Hermon area. It is an excellent aquifer and is the first groundwater reservoir of the region. Rocks from Cretaceous form 29.8% of the basin area. And the lower Cretaceous C1, C2, and C3 represent a small part of the basin, especially visible in the gentle slopes and a small portion of the northern part of the elevated crest. They cut the region.
Excuse me, Mr. Lalal. Excuse me. I am sorry to interrupt you. Are you describing geology, but we don't see it? You haven't moved the slide. Is this something we?
It is understand for I think everyone. So I can go to the next. We can discuss concerning the physico-chemical characteristics of the water samples tested. The temperature of water of sample, it was between 14 and 20. pH value was between 6.6 to 7.6. Electrical conductivity varies greatly between the minimum 313 microsiemens and 806 Siemens. Total dissolved solid level range between 250 and 600 night, with the mean value or around 450 milligram per liter. Calcium is the major cation in the study groundwater samples. Magnesium concentration range between 0.36 and
Dr. Jalal, if I may interrupt you, I'm really sorry, but I think you're not switching, like the PowerPoint is not, you're not flipping the PowerPoint. So can you please try to move the PowerPoint to the next slide, for instance, we need to test? Because we cannot see your presentation. No, it's not working. So can you stop sharing?
No, it's not working? It's not sharing now?
No, it's not working. No, it's not working. So can you stop sharing and then have the PowerPoint in full screen and then reshare the full screen mode?
Okay. I will again.
Yes, have the PowerPoint on full screen now, full screen first, and then share.
Now it's visible now.
Yes, now, okay now full screen.
Full screen. I'm on full screen now. It's okay.
Yes. Can you move to the next slide and we'll try to test?
Huh?
It's
not okay.
No. Yes. Now perfect. Okay. Thanks.
Okay. So I talked about the physical-chemical characteristic concerning the temperature, pH, electrical conductivity, and total dissolved solid. Calcium, I mentioned it. It's a major cation in the studied groundwater sample, and magnesium concentration is low. Sodium and potassium range between 0.05 and 0.86. Hydrocarbonate range between 2.8 and 6.4 with the main value of 4-5. And chloride, nitrate, sulfate, you have the concentration of this element concerning the water analysis in our samples. So I will go directly to the hydrochemical phases regarding the paper diagram for the groundwater samples of the Hasbani Basin. All the samples produced have one hydrochemical phases, which is calcium, magnesium, hydrocarbonate. One can notice that the calcic pole dominates in the region, while only few samples, especially from the Eocene, tend toward the magnesium pole. Concerning the geochemical processes, we have studied the GIPS diagram. It is very useful to understand differentiated the influences of different mechanisms especially the rock-water interaction, evaporation, and precipitation on water chemistry. The plot represent TDS versus sodium and calcium, and the other one ZTDS versus chloride and hydrocarbonate. It is divided into 3 zones: the precipitation, rock-water interaction, and evaporation. And the samples falling in the center of the curve indicate that rock-water interaction is a major geochemical processes in the region. Another point, we can notice that almost all groundwater samples for all 3 aquifers of the Hasbani Basin fall in the rock-water interaction field. Hence, rock weathering in this solution appears to be the primary factor controlling groundwater's ion chemistry in the study area. Therefore, rocks, mineralogy, and major ion concentration in groundwater have been used to understand the source of the different major ions in the aquifers and their relation to the geology and the weathering process in the region. In conclusion, this study analyzed the hydrochemical and geochemical characteristics of groundwater in the Hasbani River and the Hasbani Basin in general. This study area, which forms a part of the Jordan River Basin, is a rural area that was subject to Israeli occupation from 1978 to 2000. This is the only pump we are now authorized to take from water from the Hasbani River, only for the village of Hasbani. The results show that the major ions in the groundwater of the Hasbani Basin are calcium, magnesium, and hydrocarbonate. In the hydrochemical phases of Hasbani Basin groundwater is calcium, magnesium, hydrocarbonate. In geochemical processes that govern the formation of groundwater in this study area is mainly rock-water interactions. Evaporation did not appear to influence the geochemical processes in the area. Similarly, contamination from irrigation water is not a main contributor to the water chemistry of the region's aquifer. However, local contaminations exist, and further work is needed to investigate the full extent of groundwater pollution in the basin. And I thank you very much for your attention.
Okay. Well, thank you very much to you, Mr. Jalal. You are, again, quite sharp on time. Actually, we have a minute or 2. So this is going very smoothly. I thank you. And again, I apologize for interrupting, but we are having some issues.
No problem.
Technical issues on the slides. And we heard you're speaking about the geology and some parameters already. We weren't seeing them.
No problem.
Okay. So we'll try to be more effective next time. So, yeah, we'll keep the questions for the end of all speakers. I will have some myself. Instead, I'd like to welcome the next speaker. Actually, we have on the list we have Frédéric Huneau from the University of Corsica, but he couldn't come. He was cancelled. So instead, I will ask Joseph Arjadal, who is a PhD candidate at the University of Ibn Tufayl, to present his talk, and that is, sorry, 1 second here. There you go. Hydrogeological synthesis of the transboundary Mayo-Pliocene aquifer on the Bir Gedendous au Maroc, Boulanour, Mauritanie. So again, you have 14 to 15 minutes to present your talk. Floor is yours. Thank you so much.
Merci à vous. Bonjour. Vous m'entendez bien?
Oui, très bien. Vous allez le faire en français, donc.
Oui.
OK.
Vous voulez présenter en français?
Je sais pas. Oui, c'est correct. Français.
D'accord.
Comme vous l'avez préparé, c'est à vous à décider. Il y a la traduction instantanée ici.
Oui, je vais présenter en français, s'il vous plaît.
OK, d'accord.
Excusez-moi, je partage ma présentation. Est-ce que ça marche? C'est bon.
Oui, oui, c'est bon, merci.
Donc, bonjour tout le monde. Je vais vous présenter ma présentation sur synthèse hydrogéologique de l'aquifère transfrontalière Pliocène de la zone transfrontalière Bétel-12 Maroc et Boula-Noire Mauritanie. Je commence par une introduction. Bon, l'aquifère Pliocène, nommé aussi continental terminal, se développe dans la région de Boula-Noire en Mauritanie et se prolonge au nord vers la commune de Bétel-12 au Maroc. L'aquifère fait partie du bassin sénégalo-mauritanien, codé par le Code international de l'UNESCO par AF 58. Il s'étale sur une superficie de 3800 km². En Mauritanie, le continental terminal comprend 3 zones différentes. Bon, l'aquifère de Trarza sur 20 000 km², l'aquifère de Binchir sur 1200 km² et l'aquifère de Boula-Noire, qui fait l'objet de la présente étude, sur une superficie de 3800. Pour la problématique générale de la zone d'étude, c'est qu'à la Mauritanie, c'est un aquifère qui constitue une source vitale. C'est la seule source actuelle d'approvisionnement en eau potable pour Boula-Noire et la ville de Nouadhibou, la capitale économique de la Mauritanie. Au Maroc, le besoin global en eau de la population rurale et du cheptel augmente. Et les prélèvements futurs pour des projets d'embouteillage d'eau à Bétel-12 sont déjà envisagés. Bon, la géologie de la zone, c'est du continental terminal qui correspond au Miocène transgressif reposant en concordance sur le paléogène. Et dans la Mauritanie, elle est présentée par les grès de Kaïdi à la base et les grès de Trarza à son sommet. Il s'épaissit de l'est vers l'ouest de 20 mètres à Kaïdi et plus de 400 mètres sur la Setra d'Amcha. Bon, pour les matériels et méthodes, 750 sondages électriques verticaux sur un dispositif Schlumberger de AB6000 sont réalisés dans la zone d'étude côté marocain. Et plus de 70 forages et puits sont réalisés dans la zone de Bégen-12. La répartition des forages et puits sont construites. Bon, pour la lithologie, l'étude a reconnu une géométrie d'aquifère à 2 couches. Une couche supérieure composée principalement de sable et une couche inférieure qui est captive et qui correspond à des grès, des argiles et grès argileux. Pour la profondeur d'accès des aquifères, la nappe est atteinte à 15 mètres à la région de Bétel-12, à 40 mètres au nord et à plus de 40 mètres au sud de Bétel-12. Pour la carte des isohypses, la carte montre un léger plongement de l'est vers l'ouest. Elle présente une structure déprimée selon un axe d'orientation nord-sud. Les côtes les plus élevées sont enregistrées à proximité des affleurements paléozoïques. Les côtes des toits de l'aquifère supérieur sont de 0 à moins 250 mètres et de l'aquifère inférieur sont de 100 mètres à moins de 400 mètres. Les épaisseurs des aquifères, l'épaisseur de l'aquifère supérieur varie de 20 à 100 mètres. Une grande partie du nord du bassin refère un aquifère ayant une épaisseur comprise entre 40 et 60 parties. Bon, pour les épaisseurs les plus importantes sont observées dans le centre du bassin. Pour les épaisseurs de l'aquifère inférieur, ils sont de 100 à 300 mètres. Les paramètres hydrodynamiques des aquifères sont, pour la transmissivité, ils varient de 10 à la puissance moins 2 à 10 à la puissance moins 3 pour la nappe phréatique, et pour la nappe captive, bien sûr, phréatique, ils varient de 10 à la puissance moins 3 à 10 à la puissance moins 4. La piézométrie. La piézométrie, bon, l'écoulement, il est de l'est vers l'ouest. Bon, il est en direction à le champ captant de Boulanoir. Ici, c'est du champ captant qui alimente la zone de Boulanoir et la zone de Noailly. Le gradient hydraulique est d'environ 2 fois 10 à la puissance moins 5. Pour le renouvellement de la nappe, bon, la région est caractérisée par un climat continental hyper aride, donc les ressources en eau de surface sont relativement rares, 28 mm par an en moyenne. Bon, ces conditions peuvent exclure toute possibilité de renouvellement de la nappe. On parle d'une nappe minière. L'étude géophysique a permis de tracer la limite de biseau-salé. Bon, l'intervention des eaux de la mer. Il est de 20 km à l'est de la localité Safia et il est de 20 mètres vers la zone de Belgeret. Bon, comme conclusion et perspective, les considérations énoncées précédemment permettent d'envisager la gestion des eaux de la zone d'étude selon des voies différentes. Selon une option de conservation et de protection, celle qui consiste à utiliser de façon contrôlée les eaux souterraines, cette option est appropriée pour des petites nappes. Il s'agira de contrôler les prélèvements, de suivre les niveaux et la qualité des eaux. Une autre option d'intensification, celle qui consiste à encourager le recours aux eaux souterraines profondes pour favoriser localement le développement socio-économique de la région. Cette option est adéquate aux zones où l'aquifère profond est accessible, dans de bonnes conditions de coût et de qualité. Pour les consignes proposées pour cette étude, sont deux options. Le type réglementaire et conservatoire pour les petites nappes, c'est-à-dire limiter le prélèvement, contrôler les rejets et les ressources de pollution, décréter la priorité à l'alimentation en eau potable et l'abreuvement végétal, installer un réseau de suivi et d'observation des niveaux et de la qualité, notamment le long des côtes pour le contrôle de biseau-salé. Ces options sont de type incitatif pour l'aquifère profond, en vue de valorisation de ces ressources, c'est-à-dire appui et conseil aux usagers potentiels, établissement du cadre de zones favorables, conseil technique pour la réalisation du forage profond, etc. Il y a une délimitation de zones favorables ouvertes à la mise en valeur par des activités économiques, l'élaboration d'un modèle de gestion de l'aquifère, et mise en place d'un réseau de suivi des niveaux piézométriques, des températures et de la qualité des eaux profondes. Bon, et merci pour votre attention.
Ben, merci beaucoup, monsieur. J'ai oublié votre nom, excusez-moi. Joseph, oui. Merci beaucoup. Et pour regarder les temps aussi, je vous remercie. Oui, il y aura des questions certainement à la fin, mais personnellement, je trouvais les conclusions intéressantes, sauf que c'est pas clair dans quel pays. vous disiez il faudra l'option 1 dans laquelle on contrôle un petit peu davantage le pompage et le débit, et l'option 2, on va aller plus profond. Oui, mais dans quel pays? Ce côté-là, c'était pas clair. Mais si vous voulez, on les garde pour une discussion plus tard, parce qu'il faut aussi savoir que dans les contextes transfrontaliers, ce qui nous intéresse, c'est les échanges transfrontaliers entre deux pays. Si vous voulez, pensez-y, on reviendra à la fin lors des questions. Ça va? D'accord. Merci. Okay, so we're going back now to, I believe we have completed the oral presentations. Let me see, that is correct. And so we're going to jump into our videos now. 3, perhaps 4 videos, depending on whether everyone is here today. The first one is when our colleague, Freneno Kukuri from IGRAC, who is the Director General of the International Groundwater Resources Assessment Center, and he was here with us for the few days before, and now he will see him on the screen with his own video. So if the video is ready, please go ahead with it. And I don't see Neno on the screen.
In the last 2 decades, substantial progress has been made in the delineation and description of many transboundary aquifers across the world. Preliminary estimations of change of groundwater storage in some transboundary aquifers have been made as well. However, much less information has been collected and much less has been learned about the quality of groundwater in transboundary aquifers. A transboundary water assessment program, so-called TWAP, included an indicator-based baseline assessment of status and trend in almost 200 transboundary aquifers worldwide. 2 indicators dedicated to groundwater quality, namely groundwater natural background quality and groundwater pollution, could not be sufficiently assessed due to lack of data, covering only 30 and 10% of transboundary aquifer national segment, respectively. However, the TWAP has illuminated some processes, for example, that a very low background groundwater quality is often the result of high impact from irrigation return flows in densely populated areas with low to medium natural recharge, such as Nubian sandstone and Indus transboundary aquifer. Apart from TWAP, there were very few studies dedicated to groundwater quality of transboundary aquifers. To mention salinity mapping in the Middle East, done by UN Esquire and BGR, and nitrate issue analysis in the Abbotsford Aquifer shared between Canada and USA. Groundwater assessment, quality assessment at the aquifer scale of TBA is challenging for many reasons, starting with the upscaling of point findings at the aquifer scale. Further, groundwater quality usually changes not only with depth, but also with time. Accordingly, a possible travel time to the border between 2 aquifer states needs to be included in the TBA assessment. Differences in national legislations and in monitoring sampling procedures make the assessment of the qualitative state of the transboundary aquifers even more complex. The Friends of Groundwater, a network of about 30 global groundwater experts representing about 20 institutions and organizations, prepared a so-called perspective paper assessing groundwater quality, a global perspective, importance, methods, and potential data sources. The paper is prepared in the framework of the World Water Quality Assessment, WWQA, initiative led by UN Environment, UNEP. This baseline document prepared by FOC for the global assessment also addresses specifics of TBAs, in particular comparable standards for the aquifer, data sharing and joint capacity development programs. Some progress has been made in standardization with the European Union, although the European concept of groundwater bodies does not provide much guidance on possible transboundary impacts. Moreover, the priorities regarding transboundary groundwater quality assessment could differ per region. Therefore, the work of the FOC within the WWQA initiative should be aligned with activities of ISARM program and IIH Commission on Transboundary Aquifers and on groundwater quality.
Great. Sweet, nice, and short, to the point. Thank you, Neno. If you are hearing this, if you're listening to us, I have some questions, but if you are not available, then we will keep them for us. We have two more videos to show. Actually, two more videos to show. I'll ask, please, Christian Sieber, Helmholtz Center for Environmental Research at UFZ, a researcher who will present a video on the complex Yarmouk transboundary water resources, and he is available. Thank you. So let us show the video.
Welcome to our presentation about the complex Yarmouk transboundary water resources. This study was co-funded by the German Ministry of Education and Science and the German research community DFG. My name is Christian Siebert and the names of my co-authors are listed below. The area of the Yarmouk Basin is in the north in Jordan, and it covers the triangle between Israel, Syria and Jordan. Due to its elevation, the basin receives large amounts of rainfall compared to the much drier areas south and east, where semi and fully arid areas prevail and can be shown or observed in these pictures. That amount of rainfall makes it one of the most important ground and surface water basins in the region, being highly used by all riparian. That east geological map and profile illustrates the large water obstruction in the lower Yarmouk Gorge, indicated by red dots and black stripes, and shows the geological formations where the water is taken out. The established geological concept endorses a common transboundary groundwater resource, which implies wells along the gorge are connected to the same aquifer, and the groundwater basin is shared between Syria, Israel, and Jordan. However, if one interprets new analytical results for wells and springs in the lower Yarmouk Gorge, the picture looks much more differentiated. Taking, for instance, the stable isotopes of water and the commonly applied method of presentation, groundwaters fan out due to different recharge areas. There are isotopic light waters infiltrating in the high altitudes of the Anti-Lebanon, discharging at the northern branch of the gorge, while those emerging in the south are locally recharged in the less elevated Jordanian Ajlun Plateau. In between, there are hot springs which refer to isotopic patterns and different from the both others. Continuing with analysis of chemical solutes, taking for instance rare earth elements, the samples from the Yarmouk Gorge show very differently lithologies of recharge areas. Some recharge areas are for instance built up from limestones, others from basalt. There are just selected results to introduce into the complexity of the obviously not so homogeneous reservoir. The fully studies are cited. Eventually, a common conceptual model of the lower Yarmouk Gorge was developed, which indicates a differentiation between groundwater flow from north and south of the gorge. This is only possible by having a fold in between, which separates the groundwater bodies. To prove that concept, the 2D thermodynamic model was established by Goretsky in 2016. However, to explain the hot springs within the lower Yarmouk Gorge, which cannot be recharged north or south of the gorge, but further northeast in the Syrian Haran Plateau, that fault must be rather a fault zone, with anisotropic conditions allowing flow along the flow path, but preventing cross-plane flow. applying the known boundary conditions to water table, spring discharge, etc. That theory could be proven as well by a new 2D numerical flow model. And now we are conducting a new project with the aim to model a complex system in 3D based on innovative monitoring data gained during the project time. And with that, I would like to say shukran, toda, and thanks for listening.
Well, that was fast. That was fast. Thank you so much. Thank you so much. All right. Christian, we will keep perhaps questions for you later. Okay, so it is my pleasure now to complete this session before we go on to questions and answers with the last video from Nuaiti Nurdin, or Nurdin Nuaiti rather, who is a professor at the Abdel Malek Essaidi University. And we will show a video on the contribution to the hydrogeochemical study and water resource area of the Nekor Basin Aquifer in northern Morocco. May I have the video, please?
Donc, bonjour chers conférenciers. Donc, avec vous, dans le laboratoire de sciences appliquées d'Hiroshima. Mon intervention est intitulée sur l'évaluation de la qualité physico-chimique et des sondes de recherche de l'aquifère de Nekor, donc le bassin de Nekor, les aquifères de bassin de Nekor, donc situés du Maroc, spécialement dans la ville de l'Hiroshima. Nous avons imaginé et suivi donc l'évaluation piézométrique. L'évaluation, si vous voulez, de la carte piézométrique, donc et aussi entre 2 à, vous voyez ici, 2 à 30 mètres, donc le sens d'écoulement est généralement du nord vers le sud. Ce qui concerne l'évaluation et la qualité physico-chimique, nous avons basé essentiellement sur le diagramme de Pepper et Scholler. Donc, les faciès hydrochimiques est subdivisé en grosso modo en 2 groupes. Donc, le premier groupe, il est chloruré, sulfaté, calcique et magnésien. Et le deuxième groupe est chloruré, sodique et potassique ou sulfaté sodique. Donc, concernant, si vous voulez, les faciès hydrochimiques selon le diagramme de Scholler, donc on présente presque des profils presque identiques, à l'exception de quelques points, par exemple le point 15 et 16 et le point 2, donc, qui enregistrent, si vous voulez, des valeurs anormales, surtout en chlorure et en sodium, donc liés au lessivage des sédiments, si vous voulez, riches en NaCl de l'âge triasique. Donc, concernant le paramètre de la conductivité électrique, donc décroît généralement du sud vers le nord. Donc, les puits situés au son littoral plus touchés ont des valeurs anormales de la conductivité électrique. Donc, les valeurs liées toujours au lessivage, si vous voulez, des faciès litologiques salifères d'âge Trias. Donc, ce qui concerne le modèle, si vous voulez, et les attitudes de recharge, nous avons réalisé un module, bien sûr, qui explique le fonctionnement hydrogéologique de la zone d'étude. Donc, les zones de recharge au sud, donc situées au niveau des montagnes, aussi de barrages de Khabi, et aussi au niveau des oueds, surtout les oueds principales de Nekor et leurs affluents. Aussi, on a des phénomènes d'évaporation touchés par les eaux souterraines, mais le sens d'écoulement généralement du sud vers le nord est votre ancien.
Très bien. Merci beaucoup, Monsieur Nouyaiti. I don't know if you are available in case there are questions, but we will see. So we are really ahead of time, actually. We completed the talks and the presentations before it was supposed, but that means that we will have time for questions. If you may put the speakers.
Can we request all the speakers to turn on their cameras now for the Q&A, please? Thank you.
Okay.
My
so
Zoom
I
meeting.
have so far I have 5 questions aligning here, and I would like to begin with one question, actually, from yourself to yourselves. Is one of the speakers asking another one of the speakers, and this is Christian Sieber, who has a question for Michael Brzezinski about the differences between aquifers and groundwater bodies in the Karawanken. And I invite Michael to please reply alive so we can also hear him.
Thank you for the question. You hear me?
Yes, very well.
Okay. So it was not clear to me what kind of differences you mean.
Can you hear me?
Yeah, perfectly.
Okay. So you you showed a map about the common groundwater resource along the Karawanken, and within there were certain aquifers outlined.
Okay.
And when I got it right, you mentioned that the groundwater body, which is connected, so all over the Karawanken, is in regard to the European Water Framework Directive outlined. So I wanted to ask you, how was it outlined? And how could you differentiate between these aquifers within that resource?
Mm-hmm. So going from back to forth, these aquifers, which were defined separately, these are karstic aquifers.
Yeah.
So these are, in fact, bodies of carbonates which are connected transboundary. So these are, how to say, carbonate bodies which were very well defined due to the tectonics. Here we have a nape structure, and it is clear that this is aquifer. This transboundary water body, the question is more complicated because groundwater body, it's not equal to aquifer, according to the Water Framework Directive. And so this area was defined as an area where we will jointly manage groundwater. So it means that we have here a lithology, which is relatively complex. We have lithology from the upper Paleozoic. So there are many clastic rocks. And then we have a lot of Mesozoic rocks, which are carbonates. And then we have something also in Quaternary. And so it does not mean that this transboundary water body is one aquifer. It is management water body.
So it's an administrative border.
Yeah, it's somehow administrative, but it is based on geology or in hydrogeology.
Yeah,
so at that time where we established this groundwater body, we have a lot of discussion about where the border should be. And finally, it was not just related to hydrogeology, but it was also related to the, let's say, management practices and the ideas of both parties.
Okay, thanks a lot.
Thank you. You're welcome.
Okay, well, thank you for that first question. I don't see from the public others, but I have myself a few questions. And my first question is also to Michael or Michael. And again, as I mentioned earlier, about the nice case of cooperation, including not only science, but all the way to policy cooperation. It's really a case study that is we would like to mimic elsewhere in the world. You mentioned clearly on the different issues on the database for water management and groundwater protection, etc. But one of the things, as you certainly know, we at the ISARM and the overall Transboundary Commission, and where interests are one of the main interests is fluxes and effects of fluxes from one country to the other, You didn't say anything about that. So I was just wondering, did you evaluate transboundary fluxes? And if you haven't, just because you know the conceptual modeling already, do you have an idea on what that might mean in these circumstances?
Yes. Sorry, but presentation is just short time, and it's not possible to explain everything. Yes, we have an idea. We even have, let's say, very detailed information, because at that time we made several investigations, not just mapping, but we performed also isotope measurements. We performed also simultaneous discharge measurements. And so we have, for these big springs, we have very clear idea about the recharge area. We have also the idea about the residence times. And we calculate out from this data also where the recharge area is. So it means that we, in fact, knows, for the biggest springs, of course, from where water is coming. And this was result concomitantly on one side, tectonical and stratigraphical mapping. So we have an idea about the structure. And then based on this structure, where we have outflows from these aquifers, we measured several things on the springs. And so based on this, we investigate and, of course, interpret from where water is coming. So it means that we know exactly where water flows. And in some parts, we have even tracing experiments. So it means that we have a really direct proof that water is coming cross-border.
Right. Very nice. Well, this is important under the context, again, of transboundary.
To be honest, we have to say that this is high mountains area. So it means that it is, from natural point of view, very clear. So it means there are not much pollution. And there is also not many settlements there, because people are not living on steep slopes.
Right.
But we have some issues, of course, ski slopes, pastures, some agricultural activities, but they are not so heavy as in other parts of the world.
Okay. Thank you, Miguel. I see that there are other questions arriving from the public. I had my own. Let me just move on one of my own, and then I catch up with the other ones from the public. My second question is to Boyka. Actually, I hope she's still here with us. Are you here, Boyka? No, maybe she left. Boyka Ivanova Mihailova. Okay.
Yes, I'm here.
You are here.
Yes,
okay, thank you.
I'm here.
Yes, good. I have a question for you. Your talk was very enlightening in many senses. And again, I'm speaking on behalf of ISARM and the interest of transboundary aquifers and whatnot, and why we're trying to promote it, etc. And it became clear in your talk between Serbia and Bulgaria that for some reason, the coincidence between watersheds and the groundwater going to each country separately. So I understand. And we have defined up to 4 officially, in quotes, types of transboundary aquifers under ISARM. And this has moved on since many years now. And in your case, however, you mentioned about karst. And I'm curious what's happening, because certainly karst fluxes will not necessarily follow the watershed's boundaries or watershed's topography, so to speak. So do you have any idea on methods? Because this is one of the things that we are interested in at ISARM. So what type of methods would you recommend? I know you haven't done it because you said it's future work. But do you have any idea already on how you want to approach evaluations of fluxes in a karst-dominated system? I know it's hard. There's no standard method for evaluating karst fluxes in a karst system.
I'm here with Professor Benderev, and he will answer all these questions.
Maybe if you allow me.
Okay, yeah, sure. Okay, please go ahead. Yeah, sure.
Okay.
It's not good maybe speak in Bulgarian, Boyka interpreted for me. Райони в България. Има райони.
There is an area in Bulgaria
и Сърбия.
And Serbia.
В които има вероятно протичане на води от България към Сърбия.
Where there is a transfer of groundwater from Bulgaria to Serbia.
Има една река, Комщицка река.
For example, river Комщица.
Която много вероятно е част от водите да излизат в Сърбия, в Еловичко врело.
Where it's possible the water to penetrate in Bulgaria and appear in Serbia, in Еловичко врело. And maybe
било добре в бъдеще да се проведе един хубав индикатор.
Maybe it's possible to conduct some indicator tracer experiment in this part.
Да.
And this will be proof
както е възможно и обратното.
This will prove the transboundary transfer of groundwaters.
Okay. As I said, I'm there to ask the question, but I know it's complicated. I know it's not easy. If somebody else in the science or session today would like to say something about it, I see somebody raise his hand. I don't see your name. Go ahead, please.
Yeah, Zoran Stevanovic, I'm one of the co-authors of this Serbia-Bulgarian challenging work. The point which you ask is correct, except this tracing test. We also use groundwater budgeting as a method in order to assess how much water is flowing from which country to another. And during some longer period of investigation, even before we started this joint cooperation with Bulgarians, we accounted that, for instance, about the 6% of the water in the Serbia is arriving from Bulgarian side. This is exactly the karstic aquifer which is shared between the two countries. So it's with a tracing test and field experiments, we also take in consideration the water budgeting as a method for evaluating the schemes on which we have to use for the further exploration.
Right.
Thank you.
Right. Groundwater budgeting. Okay. Well, I leave it at that for that question. Thank you so much to the three of you. I know it was hard, but so that's why we're here, to debate and discuss things. Thank you so much. Do we have already other public questions, or I can't really read it? I do the next one while you help me, please. Okay, so I move on with I see something on the screen, but it's too far. I can't read it. So I'll do the third question of myself. My own question, sorry. And this is going to be addressed to Jalal from Lebanon. Hoping he's still here. Yes, he is.
Yes, I'm here.
So I follow your geochemistry study of the Hasbani's groundwater that you identify 3 aquifers and get lots of parameters out of that. Please understand, I'm not trying to provoke anybody. I just want the public to know that the interest of transboundary aquifers is precisely, the reasons why we study. And this theme, the topic of this conference, in this case, is advancement in the assessment of transboundary aquifers. And sometimes he has been a little bit criticized that, so we're doing a lot of techniques and jargon on hydrogeology. So my question, very simple, is so what? So now you know all those parameters, now you know all these hydrogeochemistry studies and analysis. It seems to be very rich. And so what are you going to do with it? So what in the context of transboundary aquifers?
Thank you for your question. For the question. As I have mentioned it, this is the first study carried out on the Hasbani Basin, and before 2000, the region was under Israeli occupation, and it was forbidden to do anything concerning the water quality and the water situation in the region. From 1982 to 2000, all water was discharged directly to Israel, and Lebanon has not the right to take one drop. Now the situation is under the control of United Nations and for the UNIFIL, and to do our study, we needed a lot of authorization to take samples. For the moment, we plan to do a more in-depth study on the hydrogeology of the region to explain in particular the processes of groundwater recharge and how for the moment we can calculate the hour rate from our basin, because till now Israel takes the measure of water directly to the Israel.
Okay, well, thank you. Thanks so much. I understand that. So, are we okay?
You want me to read the question?
Okay, I think it's better that Rita reads the question from the public. Go ahead.
Yes, we have a question from the audience from Michel Frem to Dr. Halawani. He asks, were the collected groundwater quality data used to assess some groundwater dynamics in terms of recharge processes, flow between the different aquifers, etc.? And if yes, what were the main conclusions in this regard?
We don't yet conducted the in-depth study concerning the all hydrogeological parameters for the region, but maybe next week we will start a new PhD on the area. But it's not so easy considering the economical and the political situation in Lebanon, and we need some cooperation with the international colleague, especially from US and France, because for the moment, France and US are our friend in the field, because as a Lebanese, sometimes we are not allowed to go to take samples. So it is a critical situation in the situation, and maybe conduct to specific crash with Israeli forces.
Okay. Well, thank you again. So we don't have any more questions from the public, but I have my own question, still my last question, and this is going to be addressed to Joseph, if he is still here with us. Are you here, Joseph? Est-ce que vous êtes ici encore?
Oui, je suis là.
Okay. Is that okay? Can I do it in English, or ça va si je le fais en anglais ou il y a traduction? Ok, so, puisqu'il y a des traductions, je vais le faire en français. Donc, Morocco, la Mauritanie, le Maroc et la Mauritanie, et vous avez bien présenté la synthèse hydrogéologique. Les cartes et les graphiques sont très clairs. Je n'ai pas de questions sur cette présentation. Cependant, vers la fin, les conclusions sont très intéressantes. Vous parlez des deux options. Alors, la première option, évidemment, vous voulez contrôler, pour ainsi dire, surexploitation éventuelle, n'est-ce pas, du point de vue de pompage. Et la deuxième option, vous dites, pourquoi pas aller plus profonde, n'est-ce pas, continuer à augmenter l'exploitation, mais des aquifères plus profondes. Tout ça, c'est très bon. Ma question, encore une fois, comme j'ai déjà l'ai dit plusieurs fois, dans les contextes transfrontaliers, quels seraient les effets potentiels pour chaque pays dans option 1 et dans l'option 2?
Bon, merci pour votre question. Bon, l'objectif, c'est de limiter surtout l'effet de l'intrusion marine. Bon, on a vu que après un pompage extensif, les zones de la mer sont toujours en avancée. Bon, pour la Mauritanie, surtout, ils ont exploité ces eaux pour l'alimentation en eau potable. Ils ont installé des piézomètres tout juste à côté du champ captant pour toujours mesurer, bien évaluer cet avancement. Bon, si en allant à exploiter la nappe captive, cet effet, il va diminuer. Parce que on a un réservoir qui est très important et on peut l'exploiter en gardant toujours les deux réservoirs en bon état et tout ça. Nous essayons maintenant d'élaborer un modèle hydrodynamique qui est partagé pour les deux pays pour contrôler ou bien savoir l'effet de l'exploitation de la nappe sur le comportement futur. Et bon.
OK, c'est bon. Vous avez autre chose à ajouter?
Non, c'est bon.
OK. Non, je sais, mais justement, c'est drôle parce que lorsque je vous ai posé la question, alors d'un coup, il y a une autre question pour vous également, similaire, pas exactement la même, mais similaire à la mienne. Et je vais vous le lire, ça vient du public. Avez-vous caractérisé l'aquifère en Mauritanie également? Y a-t-il une délimitation de l'aquifère à l'échelle régionale?
Jusqu'à présent, on n'avait pas des données de la Mauritanie. Tout ce qu'on avait, c'est la partie nord de la Mauritanie, c'est-à-dire juste la région transfrontalière entre la Mauritanie et le Maroc. Au sud, on ne savait pas exactement est-ce que la Mauritanie sont déjà achevé une étude ou bien prospection géophysique ou bien une étude hydrogéologique. On ne savait pas exactement, on a contacté les administrations correspondantes, mais on n'avait pas avoir des bonnes réponses. On essaie par la suite de collaborer avec la pays pour arriver à des solutions communes et qui auront de bons résultats pour les deux pays.
Ouais. D'accord. Bon, mais c'est clair. Donc, la réponse est claire. So we are arriving at the end of our session. I don't have another question myself, so I really like to acknowledge and thank you so much for all of you for your presentations. Secondly, for staying up to the end, and thirdly, for your very illustrative questions. And I really hope that we will continue cooperating under ISARM and under countries trying to share science and technology. And don't forget, the idea is, or the context is transboundary. So thank you again so much. And with this, I close the session and we'll thank you again. Goodbye.
Bye.
Thank you so much. I would like to invite the participants to join the last high-level panel that will happen at 2:30 in the other room. So you will need to navigate on the platform to join that high-level panel. And afterwards, we return to this room for the big closing of ISARM 2021. So hope to see you soon. Thank you so much.